Hi everybody, good morning and thank you for coming. So I'm going to give this talk about RNN sequence labeling for document parsing, and I'm going to show how do you implement a simple model to do this in Tensorflow. So first, a small thing where I'm from Texas and Amsterdam, as you just said. And what we do is we try to match people to jobs by parsing their CVs, their resumes, building up a profile that way, and parsing vacancies, and then matching the extracted information from those vacancies to those people. So that's, when you see document parsing here in the title, that's what I'm talking about. So just a quick check. Who here does not know what TensorFlow is? It's okay, just raise your hand. Okay, so there's some people who didn't work with TensorFlow before. Everybody here knows what a recurrent neural network is? If you do know what a recurrent neural network is, please raise your hand. Okay, so most people, that's good. So this talk is on the novel level, but I will probably not explain like the basic RNN or TensorFlow too much. So I hope I'm on the right level for this crowd. So the document parsing part, this is our CV, and it's in Dutch, and it's way too small for you to read. But what we want to do is we want to take this kind of unstructured text. I mean, it's free form, but it's sort of semi-structured. And we want to take this and output structured information. So we want to extract what somebody's name. So here you see Petra is a first name, Van de Ven is a last name. These are just substrings from this document, tagged as being a name or a last name, or as being a job title, a data company to extract people's work experience in order to match them to a correct vacancy. So the input are these documents in PDF or rich text, and we normalize them, and we try to extract this information. So basically, like I said, these documents are semi-structured, so we have two sequence labeling problems. One of them is to extract these sections because, like I said, you can't read this document, but if I ask you where is this person's personal information, you can probably point to the correct part because everybody writes their resume in sort of the same way. Same for work experience. So we extract these sections, and then what we're going to talk about today is how do we take a section like this and extract the relevant information. So how do we label this phrase as a date, office manager as a job title, CTB Flex Software and Services BV as a company, and Ede, which is a city in the Netherlands, as a location. So what we have here is a sequence of words, or a sequence of tokens, and we have a sequence of labels, namely the first three words are date, the next two words are job title, the next word is nothing, and then there's a bunch of words that are company. So that's what I mean with sequence labeling. If these days, if you say sequence labeling, what do you think? Well, recurrent neural networks. At least that's how I work now. The two most common problems are named entity recognition, which is very similar to this. It's recognizing people's names or company names or locations in running text. And part of speech tagging, which is labeling words as a verb, noun, pronoun, all these kind of things. So the way that you do this, a recurrent neural network, you have this sequence of inputs. Then you have a recurrent neural network layer, your hidden layer, and each computational node is dependent on the previous word, or in some cases on the next word. This is like a very global idea for like the two persons that raised their hand, that didn't raise their hand when I asked who knew recurrent neural networks. But I'm going to assume that this is sort of familiar. Is that correct? Like, yeah, I see some nodding. Yeah, good. In that case, you're going to have fun at this talk. Because what I'm going to show is, what we did, we applied this kind of methods to our problem, because it's very similar to named entity recognition. And we developed some methods that are very specific to our domain. We're not going to talk about that. We're just going to talk about how to make a simple model that you can later expand to your own domain. And the old way of doing this would be hidden Markov models and conditional random fields. And that's what we used to apply. And going from those old-fashioned linguist models, or like computational linguist area models, to these deep learning recurrent neural networks, we saw a good error reduction, like 30% less errors. We were very happy with that. But me being part of the team that implements this, the thing I'm really happy with is that these models are a lot more flexible. This hidden mark model, like, you'd only use it in one way. But with these neural networks, it's very easy to make like a multitask model or change the architecture to have like different types of input. And compared to the conditional random fields, they're just a lot less feature engineering. Conditional random fields, we just write all these rules that might use in order to extract these words, and it would combine them. Writing these kind of rules manually just isn't much fun. And now you just give it more data and it starts doing better, and that's a lot more fun because somebody else texts the data for us. Okay, so some qualitative differences. If you take like a hidden mark model, it's very like always taking the same words, like power plant fitter. It's seen that before. That's probably job title, but that doesn't really help you if you don't know like where are you fitting this power plant into. And this recurrent neural network is a bit better at learning to extract like subphrases and extracting from running text. So the old model might only see a job title if there's a clear context. These models are a bit better at like these ambiguous context. And also, if you have something like, I was reporting to the general manager is not your job title, so our annotator wouldn't annotate as a job title. And with enough data, the network also learns this kind of context. So in this talk, we just had this introduction. We're going to show how to make a simple LSTM sequence labeling model. Quick side note on how to serve it if you want to do it in a hacky way. And then some of the challenges that you have to face after you have this simple model. How do you actually adapt it to your domain? And how do you solve like some of the common problems with these models? I'm just going to sort of go through the problems and leave it to you to solve it. So LSTM sequence labeling model. Who here never heard LSTM before? Okay, so that's more people than I expected. Basically, it's short for long short-term memory. Basically, it's a recurrent neural network. The only difference is if you have a normal RNN, you have this multiplication on the previous state. This model is built slightly different in such a way that you don't get this big sequence of multiplications back into time, which makes it a bit less susceptible to this vanishing gradient problem. On Cola's blog, there's a really nice example understanding LSTM networks. I would say just Google that if you want to know this. Yeah, it has really nice visualizations. So for named entity recognition, sequence labeling, there were these bunch of like nice papers and the slides. By the way, you can find the link in the program. I added it this morning. And what we are going to do is show in Tensorflow how to implement a simple version of the same kind of network that's in these kind of papers. So again, we had this input, sequence of words, sequence of labels. So your training data looks like this. On the left, you see these normalized tokens. We don't want every date to be a different entry into our vocabulary, so we normalize this. And then on the right, we see begin, inside, outside encoding. So the B is for begin, it's the beginning of the date, and then inside the date, beginning of the job title, inside the job title, and O is for outside, which means just anything else. So you create a lot of data in this way, and then we're going to feed that to our network. So, is this readable in the back? Yeah, good. What do you need for this? TensorFlow, NumPy, quite simple. How do you start? You start with some hyperparameters. This is some random example. I just put in some numbers so that we can get this code to work. What you also need is your pre-trained word embeddings. Just download them. Use whatever is normally good for your domain. try a bunch of them. Here we just have random embeddings. That doesn't work so well unless you tune it. But what you need is this embedding vector, which is the size of your vocabulary by your embedding dimension. So each row in this matrix is a word vector for that specific word in your vocabulary. So how do we start this network? I showed you what the input data was. We need to make some placeholders in TensorFlow. So for whoever said, like, oh, I've never heard of TensorFlow before, it's basically a graph computation library. You define operations and you chain them together. And then in the end, you want to get your prediction so that output then calculates back what it needs in order to calculate its output. And then the really nice thing about it is it also has auto-differentiation. So once you calculate its output, you can get your gradients towards the variables that you specify. And that means that you can train a neural network with it. So here we have X, which is a placeholder operations, which means that it's some place where you can pipe your data to. And this is a shape of like how big is your batch by how big are these sequence lengths. And you also give it these sequence lengths because you have all these sequences, these sentences or these documents of different length, and you pad them. And in the end, you don't want your loss function to be affected by these padding characters. So we use this sequence length information to mask that padding out later. And then, since TensorFlow is really built for making neural networks, it has all these really handy operations, such as embedding lookup. Basically, just replaces every index in your input vector, which are just the word index into your vocabulary by the corresponding word vector. So you end up with a batch size by your maximum length by your embedding size tensor. If there's anything like really unclear, just raise your hand and then we can do some quick questions in between. So just to show how the graph looks, if you visualize this, oh wow. I'm reading this in VirtualBox, it's not very quick. But what you see here is this embedding tensor and the input words. Here's sequence length, and here this is a variable which is just holding that big embedding vector. So how do we define a simple LSTM network? Again, TensorFlow to the rescue. You just have a basic LSTM cell. And if you're doing these kind of things these days, what you want to do is you want to add dropout to it, which is a technique for training networks. I think it's best not to go into it now, but I just added it to this example so that when you run it, you get a bit of a better, less overfitting network. So what you'll notice here, this basic LSTM cell, the only thing that you need to give it is how big is its hidden state. And the other thing you'll notice here is that this is not connected to the network yet. So this BLSTM cell is just defining the structure of your cell. Now, if you want to actually connect this to the network, what we want to do is we want to do one RNN that reads text left to right, one RNN that reads text right to left, and then concatenate the outputs of those. Because if I see some job title somewhere, and then there's a clear company name after that, then it's good to know that the next word is a company name, so this is probably the end of the job title. So here we just define that cell using the function that we defined in the previous code snippet. And then TensorFlow has several ways of defining RNN. My favorite is this one, bidirectional dynamic RNN. So there's a dynamic and a static version. A static version means that you have this unrolled network over the entire sequence length. Dynamic version means that it's implemented as a while loop, which will go over the tokens depending on the length of your sequence, so it will skip the padding characters. So it's a bit costlier to define, but like when you're running it, it's more efficient. So I'd suggest this one or the multi-layer version of this. Anything else here? Oh yeah, one thing you need to know is that you need to give it a scope. So TensorFlow is organized in name scopes, which basically means like any variable underneath one scope are not shared with other scopes. This function uses this standard scope, which means that if you use it multiple times, you'll end up reusing variables by accident. Usually somebody put in a guard for that, but if you get these errors about, oh, I can't do this because this is already defined, but reuse is not set to true, you just need to pass it a scope explicitly. And then in the end here you see we concatenate those two by df.concat. Any questions so far? Right, so now we're going to make this network. We input the word embeddings that we made in the second snippet. And then for the second layer, we just say like, oh, the input for the next layer is the output of this first layer. And that way you are stacking these bidirectional layers. So like you see here, the embeddings and the sequence length are the input for these BLSTM layers, bidirectional layers. And the input of the second layer is the output of the first layer. If this is going to cooperate. Inside this layer you see there's this forward and backward operation. And the way that this backward thing is defined is just like you reverse the input sequence and then you apply exactly the same cell and then you reverse it back. Okay, so we are at this state. We feed in this sequence of characters. As an output here, we get this concatenated vectors for each token. Now we want a label for each token, right? So we have this basically a feature vector, and we want to turn it into a label. So how do we make these predictions? It's quite simple, really. If you just treat each token independently, so each word independently, you just say like, oh, I want some probabilities for each class for each token. So what you can do is just a linear combination of this and feed that to a softmax function. So layers.dense is just a single feed forward layer. If you don't specify your activation function, it's a linear activation. So basically this is some weight matrix times your feature vector plus your bias. The only trick here is if you're working with this RNNs, which have this batch size by sequence length matrix, but you want to apply this to each word separately, you just reshape it in such a way that you have one long sequence of words by this feature vector size, and then you apply it and then you just reshape it back. And for that, all you need to know is, oh, what's this original size of this matrix? And if you apply a softmax operation to this, you get your normalized probabilities. But if you just want your predictions, you just take the highest of these logits. Questions? Okay. So you have your output predictions, but now you want to train on this. And like I said, Tensorflow allows this gradient-based training. It has a bunch of gradient minimizers initialized. Specified, like Adam, but also like stochastic gradient descent, all these kind of goodness. But we don't want to train on these predictions, because if you take the gradient of your argmax, you're going to be pretty unhappy, right? So we have a multi-label classification problem. So what you have is a probability for each class, and you have your true probabilities for each class, which mainly is the class that you want it to be. Your example in your data has this assigned class. The probability for that should be 1. Probability for the rest should be 0. You just want to have a smooth function that you can train this on. So what you say is, we take the cross entropy between these two distributions. And then Tensorflow has this sparse softmax cross entropy with logits. What this means is that the sparse part is just your labels can be the labels as just a class number, instead of having to have this one-hot encoding. So this is scarier than it looks. It's actually not a sparse operation. It's just labels, label format. Next, like I said at the start, we don't want these padding characters to influence our loss. So I use these secret lengths to make a mask to mask out the padding characters. And then you apply it this way. And then you take your mean over all the tokens. No questions so far? So what we do here, you pick some optimizer and some learning rate. Here I just take Kapati constant, but probably you want to pick this carefully and tune it. And if you have a look at this graph.
Sorry, can you go back before?
Yeah?
What's the purpose of using Boolean masks?
Right, this one, right? So your input sequences is like each row in that matrix is one sequence, and some sequences are longer than other sequences. So the shorter sequences, you put them all in the same matrix and you just end up padding them with zeros. Right? These predictions make some prediction for those padding characters. You don't want those predictions to be taken into account in your loss function. So you just mask them out, and then you take the mean. Yeah? So one nice thing you can do here, clean up your graph. This defines your loss function based on the logits and your sequence length, so you can do the sequence masking. And then this basically is connected to everything because it calculates gradients for all your variables. For example, here we see this dense layer that has your bias and your weights vector. Both of those get, this is probably too small, but the thing I'm pointing here is the train step, which is feeding gradients to this. Okay, so
what are the labels of that being predicted? So you have two kinds of labels. You know, if it's a name or a job title versus the inside-outside.
right, so basically like inside, outside, begin. If I have begin job title and inside job title, for this as multi-label classification problem, you just treat them as two separate labels. That way the begin can have like, you can learn about context. And this just, it's just the label number. So if begin job title is 1, inside job title is probably 2, outside might be label number 3, and then you just compare these.
So how many labels in total
That depends on your learning problem, but like,
In your case, like.
so we have a bunch of models that all predict specific phrases. For work and experience, it's like 5 different types of phrases. So then you have 10 labels plus outside is 11. Usually it ranges between anywhere from like 6 to 20 or something. So it's not like really large amount of labels. It's quite manageable number of classes. Okay, so we have this loss defined. How do you train this in TensorFlow? One thing you might want to know is like, oh, how is my loss decreasing? The examples I was showing where you could see the graph visualization, that's called TensorBoard. It's really nice. It can also show graphs. So with each batch, I want to show my loss function. It's a one-liner in TensorFlow, and that's basically the whole reason why my team is using TensorFlow, because it's so nice to visualize everything in TensorBoard. So let's say we make some random examples with random output. We make 1,000 examples. We sample a random sequence length, and then we make some random examples and random outputs of that length. So this is not something that you would normally do. This is, again, random stuff to get some example to work. In my notebook in VirtualBox, which is slow, so that's why I didn't take a real data set. But if you want to train something like this, you have these 3 arrays. You have your array with your sequence length, you have your array with your number of examples by their length, and you have your array with the labels for each token. You make a generator for this, so here it just yields a batch of input sequences, a batch of sequence lengths, and a batch of your training labels. And if this will scroll down, yeah. What you see here, we make a TensorFlow session. Our graph is already initialized in that session. That's what all the other code was building, this graph. One thing to do is this global variables initializer. What that does is you have all these variables defined, like your weight variables in your LSTM and in this dense layer. You just initialize it to their initial state. Another nice thing about TensorFlow is that many of these things are defined in such a way that their initial state makes sense for training. So you didn't see me specify them anywhere. Then what we want to do is we want to write out these loss functions in this case. You also want to save your model probably. And then we just loop over the number of epochs, and we loop over all these batches. So we have the input, the length, the labels, and you create a feed dict for your model. So in the very first cell you saw us defining these placeholders. This is how you fill those placeholders. So x here is still the variable pointing to the tensor. The next batch is just this NumPy array that you feed in. Then you run this train step, and in our case we also run this train summary because we want to see it in TensorFlow, and you just do this for all the batches that you have. And even though these are random examples with random outputs, you can see it's still more than happy to just memorize all your examples and decrease the loss function. So I would say, like, if you're following along with this at home later, if you're making like mistakes in your graph, just debug it here. Make sure that you visualize as much as possible here, so that you see how your training is doing. Compared to what we were doing before with like putting these things in our own log files and making our own log formats and everything, TensorFlow had such a big improvement over that. Not just because it helped us get rid of all the inner mark models and CRFs. So let's go back here.
You need to clear the memory of the
No, you don't need to in this case. Like you mean like the hidden state from the previous?
Yeah, reinitialize states, the internal states.
No, you don't need to, because when you do the forward computation, it doesn't use that state. It has a 0 state, which you don't need to initialize each loop. Does that answer your question? Anything else before we jump to like something very different of the code?
Well, I suppose we don't use this new shiny data API from Tensorflow. What about performance? What about lifecycle of your network? What about performance putting data inside the GPU?
We can talk about that just after the thing. I just asked the questions again at the end. But, or I'll remember and I'll get back to it. Okay, so if you're like us and you have this huge Perl libraries and you need to integrate these models into this, there's a really nice TensorFlow serving library. You probably want to use that in order to serve your model. But if you want to hack it into your Perl pipeline and you don't want to implement gRPC in Perl, just build a Flask server around it. The main thing to know is if you use the save model format. Oh, I can't select text here like I could in the notebook. The TensorFlow config predictor from save model, it gives you a very simple API to get predictions back from your model. So it's really as simple as that. This is a working example of a Flask server serving this model that we just trained. But if you're putting stuff in production and you do not have this old pipeline, really use TensorFlow serving for me. So let's say you have a sequence labeling problem. You take this example and you get everything right and you train it on your data. Why is it not performing as well as you hoped it would? One thing is tuning. Like I said, learning rate and optimization algorithm is very important. Which word factors you use? Do you want to tune the word factors themselves? How big is your state size? I mean, you want it to be bigger at least than the dimensionality of your word embeddings, because if you're thinking about classifying tokens and you have this embedding space and you want to make tokens separable in that space, you probably want to have room in order to transform the space in such a way that these things are separable. Next thing is, like if you have a domain like we have, you're probably going to have multilingual documents or multilingual sequences. So you want to do something clever in order to handle that. If you just use your Dutch word embeddings on this English text, you're not going to be happy. Most of the examples that I gave, the papers that I linked to, a lot of them use condition random field as output readout. So basically, instead of treating each token as a separate classification, you want to get the most optimal sequence of classifications for your sequence. So you can still basically use the output of this network as the potentials for your CRF and just add the probability of going from one class to the other class. TensorFlow also has this built in. It's an exercise for the reader in this case. And if you want to do stuff, like I said, where you want to get these sections out, in this case you have a sequence of lines, and you want to classify lines, but you need some line embedding. One option is to just put in another layer of RNNs, which go over each line, and then like do max pooling or something, and get the output from that, and feed that to the following BLSTM layer. You can use convolutional neural networks, or you could just like take the mean over all the words, something like that. But it really, all these things have a big impact on your on your output accuracy. So if you want to know like how we at Textkernel solve these things, look at our career website. And if there's any questions, I'll get back first to yours. But first, thank you for listening. So first question, do you want to repeat it in the mic maybe? Since now we have a mic. Sorry for all the people on YouTube. I didn't.
Thank you very much for the talk. Very nice to see something like that. People use it in practice, in production. Very encouraging, inspiring. And what about, I spotted you don't use this data API from TensorFlow, which is much more efficient. You use generator. What about performance of training? So what batch size do you use? And how do you put this data into the, like, what is the performance of putting this data into GPU?
Right, so one note on that. First off, if we quickly scroll up here, if you are doing this on GPUs, so we had this whole infrastructure for training our hidden Markovs and conditional random fields, which is all CPU based. And we wanted to reuse that infrastructure. So most of this is actually trained on CPUs. If you want to do this on GPUs, don't use this LSTM cell. Use the QDN variant. In that case, you definitely want to use the data API to feed inputs, and you want to just tune your batch size in order to get maximum utilization of your GPU. And you probably want to tie the word embeddings to CPU so that it's not interfering.
Which batch size do you recommend, like scale? Whether recently read article that big batch size are also best for training?
Tune it, like try the batch size, because it's really dependent on your hardware and on, like for the CPU we use like between 32 and 128 or something. It doesn't matter so much. For the GPU it is very important.
Just a really quick question. So thanks for the talk. I saw your link for the slides, but is there a link to the notebook as well? Is that available?
Probably not. Like currently the company policy, it's still getting reviewed, hopefully later, but maybe not.
Okay, so you mentioned you got like 10 to 30% reduction in error. So can you basically break it down, like in terms of which classes it worked for best, like job titles, which one of these was better improved by your technique, and how much training data did you need, and how did you collect the training data?
Okay, so I'll start with the second answer first. How much training data do you need? These are very long sequences with a lot of classes on them, so there's a lot of information on them, so not that much, like a few thousand documents was enough. So that's the nice thing about the sequences. If you have a lot of labels, there's still a lot of information in that. How it worked best? Best is to, these numbers don't say everything. You want to look at those qualitative examples, maybe. So what I showed for job title, those were really good improvements. We didn't notice that there was a certain pattern in for which fields it worked better than others. But yeah, maybe come find me afterwards later. And then, yeah.
We have time for one more question.
Thank you. You mentioned the CRF bit quite briefly at the end. I wasn't sure, does that get trained jointly with the RNN, or are they just two separate modules? Yeah,
TensorFlow has like this implementation for CRF, so basically you train the transition probabilities as well as the network that's giving you the potentials. So they're trained jointly, you just need to use a different loss function. Right?
Thank you for a great talk. And that's it.
Thank you.